So what I did was as some of you were emailing me with ideas for your projects, or what you kind of already plan on doing, it became pretty evident that a lot of you will be using some kind of regression model rather than just like an ANOVA, for example. So because of that, so I know I've sent links or example code to a few of you. So since there are enough of you, and I think, and I didn't post example code. So what I'll do is go over an example of running a chi-square test, logistic regression, and then a linear regression, because I think at least one of you will be using linear regression. So I'll go over that. I'm going to use the NHANES data set that we created in exercise 2 to kind of give you an example of how to do those. So let me turn off my video and then open up R. So you guys don't need to open up R. You can just watch what I'm doing, and I'll kind of go through the example and explain how to interpret the output. And then I will post this code for you to use for your own final project. And then just a reminder to send me, if you haven't already, your research question by the end of today. And then if if you're still kind of not sure if you're, kind of formulating it, properly, that's totally fine. Just send me an email with sort of what your idea is, and we can kind of come up together with a research question together. So, okay, let me share this. Okay. All right. So can everyone see my screen?
Yes.
Okay.
Yes.
All right. Let me open up the chat just in case you guys have questions while we're going through this. Okay. So, all right. So I'm just going to load that merged data set. So we took, I think it was 4 or 5 NHANES data sets, and we merged them together. And then we created this NHANES data. So I just kind of made up a research question that we could ask using these data. And then remember, we created this general health variable. It was poor, fair, good, very good, and excellent. And then if you remember, we created this binary variable where fair and poor were combined, and then good, very good, and excellent were combined into that second category. So, I decided that we would look at general health, and then our research question is, does general health differ by race and ethnicity? Okay, so typically in a logistic regression, we think of the 1 being representing our event, and usually an event is something that's bad. So for example, in a lot of the research that I do, an event might be a death by suicide, or someone has depression, or someone has cancer. So those are all sort of these adverse outcomes, right? And typically that would be considered our event. And then we would code that as a 1. So 1 being, yes, they have that event. And then 0 being, they don't have the event, or it's something that's actually favorable because they don't have this adverse health outcome. So when we're looking at general health, if you remember from exercise 2, we coded excellent, very good, and good as 1. But in this case, what I did was I am going to reverse it so that 1 represents this poor or fair general health. So it kind of aligns with how we typically would code an outcome, a binary outcome. So at least for something like this where, it's our outcome variable. So in this way, I'm coding it such that 1 represents our sort of adverse health group, or individuals with poor or fair health. And then all the 0s are individuals with good, very good, and excellent health. So that's what I'm doing here. I'm creating first this new variable called new health. And then I am collapsing those 5 categories into 0 and 1. Okay. All right, so now we have this new health variable where 0 is a good outcome, so that it's kind of like they don't have the bad outcome, and then 1 is the bad outcome. You have fair or poor health. Okay, and then if you remember, we added labels to the to the new variables that we created, and then to these categorical variables, we use this function factor to tell R that it's a categorical variable or it's a factor variable. Otherwise, it will treat it as a continuous variable. Okay. All right, so sometimes I get these warning messages, but it still works. Okay, let's see. All right. So the first thing I'm going to do is just kind of look individually at the new race variable, which we had also created for exercise 2. And remember, we're asking, does general health differ by race and ethnicity? So our dependent variable is our general health variable. And then our independent variable, our primary independent variable of interest is race and ethnicity. So what I'm going to do is just kind of first look at the distribution of that, right? And we did that in exercise 2. So we have about 5,600 individuals who are older than 20 in our sample. And then it looks like, you have an almost even distribution between white and Hispanic individuals, and then slightly fewer numbers of Black and other race ethnicity individuals. Okay, and then the other thing I wanted to do is just look at a summary of the general health variable that we created. So it looks like most people are in this good, very good, excellent category, about a third. So this would be like maybe 25% and then 75% if you ignore the missings, right? And then it looks like we have about 700 missings. It is again like good practice to remove these individuals with missing values. So typically what we would do, I don't do it here, but R will actually just ignore those individuals. But typically what we would do is similar to what we did for the moderate activity. So if we have a primary independent variable, and then we have our outcome variable, and any individuals are missing those values, we typically would have to exclude them from our analysis unless we impute that missing data. The reason being is those are sort of like primary variables of interest, right? So if those individuals are missing data for either of those two variables, we can't really evaluate them or use them in the analysis. And actually, as it turns out, if we include additional variables like covariates in a model, so let's say we're interested on not just in race, but we're also going to include something like age and gender, if values are missing for those variables, so for those covariates, we would also typically have to exclude those individuals. So in most analyses, we would exclude those individuals with missing values, but there are also methods to impute those data. Most often we would use what's called like multiple imputation. But yeah, so for this class and for most classes, you would just end up excluding those individuals. So these 739 people will be excluded from any analyses using this variable. Okay, so I'm just going to load the Arsenal package so that I can run this table. And that's just to give me like a summary. And you guys have done this before. So it's just a summary. So in exercise 2, we looked at the different characteristics of our population, and then we stratified by gender. So we had male, female, and then total. In this case, we're interested in looking at general health as our outcome. So typically in a table 1, we would have these sort of demographic characteristics of our sample and maybe other characteristics like clinical characteristics, for example, and then we would stratify on our outcome variable to see if the distribution of those different variables differ for the group that has an event versus the group that does not have an event. So let's say, I think one student is looking at cardiovascular disease. So you would have here in your column, you would have cardiovascular disease, yes, no. And then in this column, you would have demographic variables, and you might also include some of the exposure variables of interest. And this is typically what we would do for most table one. So any paper that you read, it will have something like this, and maybe just the total column. So it's just describing your overall sample. But more commonly, you would have a distribution of your total sample, and then they would stratify by some variable of interest. So that is your typical table one. And something that you will definitely want to include in your final project. Okay, so I've generated this table one, and then the nice thing with that table by function that I've used to create table one is that it also spits out these p-values, and it will do, it'll run the appropriate tests depending on what kind of data I'm looking at. So for this comparison for gender by general health, it's going to run a chi-square test, right? Because I have two categorical variables. For age by general health, it's looking at mean age, and then looking at an independent categorical variable. So it's going to run an independent two-sample t-test to give me this p-value. Okay, and then for this, when I'm looking at race by general health, it's also running a chi-square test because I have two categorical variables. So, so that's the nice thing with R. And then if we were to interpret this, we would say, in our sample of, about 5,000 individuals who have a non-missing value, right, for general health, there appears to be no difference between men and women with regard to general health, because that p-value is greater than 0.05. So yes, so we fail to reject the null hypothesis that there's no difference. So we conclude that there's no difference between men and women with respect to general health. On the other hand, our p-value is less than 0.05 for age. So when we're just looking at that single comparison, age and general health, it looks like mean age does differ by general health. And it looks like individuals with poor or fair health tend to be older, statistically significantly older than individuals with good, very good, or excellent health. And that makes sense, right? Because as we age, some of these like chronic conditions and health, adverse health conditions, those all tend to increase with age. So that makes sense, right? And then here we would say, there is a statistically significant difference in general health by race and ethnicity. And then we can go on to kind of describe, like, it looks like, a greater relative proportion of white individuals have good, very good, or excellent health, whereas, a greater relative proportion of Black and Hispanic individuals have poor or fair health. Okay. And then another thing to note is that these are just univariate comparisons. So it's just looking at two variables, these are bivariate comparisons. So we're looking just at gender and general health, for example, age and general health, and then race and general health. So we haven't yet gotten to the point where we're running an actual model to look at, for example, race and ethnicity and general health, adjusting for all of these other factors or keeping those other factors constant. So we haven't done that yet. Okay, so the first thing I want to show you is how to create just an R by C or a row by column table. So in this case, it's a 4x2 table because we have race, 4 rows for race, and then 2 columns for general health. So this is I'm just showing you different ways you can create this table. So one is using this with function, and then you can see just a nice 4x2 table here. The other option is using a table function. Okay, and then as you can see, you get the same exact result. Okay, so what I'm going to do is take this object that I created for the 4x2 table, and that's where I'm going to use this chi-square test. So this is a chi-square dot test function, and then I just put in that object that I created up here. And then when I run that, it runs the chi-square test for me. So the nice benefit of this is just being able to look at the specific variables that I'm interested in rather than running this, whole table by function and having this larger table just to get that p-value. But you'll still want to keep this in your, your repertoire so that you can create table ones for your final project, and I'm almost certain you'll create a table one for your thesis, as well as any publications that you have in the future. It's such a standard table that we would include in most of our publications. So, okay. So if you remember from the table, the p-value is less than 0.001, and sure enough, it's a very, very small p-value. So how would we interpret this? So the p-value is less than 0.05. So we reject the null hypothesis that there are no differences in general health by race. And so we would then conclude that there are statistically significant differences in general health by race and ethnicity. Okay, and then just like I showed you with this, with the larger table, you would say that, and then you could go on to kind of describe how race and ethnicity are distributed within those two groups. And we can see that they are different. Okay, so let's see. All right. So again, that comparison is just a bivariate comparison. It's just looking at those two variables. But if we think about health, right, especially when we look at our table, let's go back to table 1. Age was statistically significantly associated with general health. And that makes sense, right? As we age, we are at greater risk for some of these adverse outcomes, or, we're at greater risk for having poor health. And so maybe age is something we want to adjust for in our model. The other thing that we might want to adjust for is gender in a model. So in this bivariate comparison, there is no difference in gender with respect to general health, but maybe, maybe men are at greater risk of, certain outcomes, and women are at greater risk for other outcomes. And so it is a potential confounder, right? And I think, as I mentioned last week, there are these sort of very face value confounders. So those tend to be gender, age, and race ethnicity. In this case, race ethnicity is our primary exposure variable of interest, or our primary independent variable. But gender and age are typically things that we would control for in most of our analyses when we use models, just because they do tend to affect a lot of health outcomes and are also associated with a lot of exposures that we might be interested in. Sometimes it's not the case. We might run a model and show that they are not associated, they're not, significant confounders, and then we would be able to remove them from our model if we wanted to. And then other times, some researchers will still leave them in, even if they're not significant, just to show reviewers and anyone reading the paper that they had considered these, as sort of very standard variables to include as potential confounders. So we typically would include them in our model. Okay, so I already loaded this package. Let me just scroll down. Okay, all right. So what I'm going to do then is run a logistic regression where I'm looking at any potential effect of race on general health, but controlling for these other factors. Okay. So the general sort of syntax for that is I'm going to create this object called output, and then I'm running this generalized linear model. And so remember, logistic regression is still part of this family. It's just that we're transforming the outcome variable so that we still meet that assumption of a linear relationship. So this is sort of the basic. We're saying our formula or our model, we have our outcome variable, and then we have this like tilde, And then we include all of our independent variables. And if a variable happens to be categorical, then we would use this function factor to let R know to treat it as a categorical variable. So we actually already created like new race and general health, for example, and already created them as factor variables. But just for completeness, we'll still include this factor function within our GLM function. Okay, so then in this case, variable 3 happens to be a continuous variable. So we don't need to use the factor function there. So for example, that might be age. Okay, then we specify our data set name and then our family. So what, I think I used the term link last week. So what family of model is this within the broader generalized linear models? And in this case, it's binomial because we have a binary outcome, right? We have general health. It's like yes, no, is it poor or fair? 1 being yes, and then 0 being everybody else with good, very good, or excellent health. Okay, so I think the default is actually a linear model, so it would not have any transformation there. So if you were to leave it blank, it would run a linear model. So we specify binomial to tell R we're running a logistic regression. We have this binary outcome. Okay. So now let's run our actual model. So we have this GLM function, and then we have new health, which is our binary general health variable. We're looking at race as our primary variable of interest. Okay, so in this case, I'm running just a model that is not adjusting for any other factors. Okay, so this would actually be pretty equivalent to the chi-square test actually, because I just have those 2 variables. Okay. The difference here is now we can actually look at, so remember we had, let me scroll up. White was 1, black was 2, Hispanic was 3, and then 9 is other. So the way R will treat this is that first category is your reference group. So basically what a logistic regression will do is it'll say, how do blacks compare to whites? How do Hispanics compare to whites? And then how does this other race ethnic group compare to whites? Okay, and so that's why you don't see a row here for white. You just see black, Hispanic, and other. The reason being is that we're comparing black to white, and then in this row, this is Hispanic to white, and then other to white. Okay, so remember for logistic regression, we are estimating odds ratios. But if we just run the model, R just gives us these estimates. So these are our beta estimates. What we have to do is exponentiate these in order to get our odds ratio. So let me go back to our code. Okay. Hold on 1 second. Okay. Sorry, I put this question in here to remind myself. So how many values, how many observations were removed due to missing values? You can see that here. So remember, we had 739 individuals who were missing general health. So they were not included in this analysis. So this is good. We see 739. That's the same number of individuals that were missing general health. So we know that, everything was done properly by R. We've removed those individuals. There weren't any additional, exclusions. Okay. So then again, we have to exponentiate these estimates in order to get our odds ratio. One note is that if the estimate is positive, that is going to correspond to an odds ratio greater than 1. And if it's negative, so like, for example, here, that is going to correspond to an odds ratio that is less than 1. If it's 0, then it would correspond to an odds ratio of 1. All right, so let's get our odds ratios. So the way we do that is we're going to create an object, and here I'm just calling it odds ratio, and then you're just exponentiating these odds ratio output, or sorry, these coefficients from our model object. Okay, and then in addition to that, we are asking R to give us confidence intervals. So this function is taking the coefficients and giving us our odds ratios, and this function is giving us the corresponding confidence intervals for those odds ratios. Okay. All right. So now if you look down here in our console, now we have our odds ratios. You can see like it's a lot of significant digits. So in order to clean that up, we can just round it to 2 digits. So that's what I'm doing here in line 82. And now this looks a lot more, manageable, right? So this column corresponds to our odds ratio. This is our lower limit for the odds ratio, and this is our upper limit. So this is the lower limit for the 95% confidence interval, and this is the upper limit for our 95% confidence interval. Okay, so if we were to repeat this experiment over and over and over again in different samples from the same larger population, we would expect that 95% of the time, our odds ratio would fall within this range, 1.46 to 2.12. Okay, it doesn't mean that we're 95% confident that this is the correct answer. What this means is if we were to repeat our sample over and over and over and over again, like an infinite number of times, 95% of the time, our odds ratio would fall within this range. Okay, so that's how we would interpret that 95% confidence interval. So how do we interpret this table? Okay, so remember whites are our reference group. So in this case, the odds ratio is greater than 1. So Black non-Hispanic individuals are at a greater risk, or they have a higher odds of having poor or fair health compared to white individuals. Okay, and then we would say they are at 76% greater odds of having poor or fair health compared to white individuals. For Hispanics, it looks like, so it's almost an odds ratio of 3. So it's actually quite a large odds ratio. So we would say in this case, Hispanic individuals are almost at 3 times greater odds of having poor or fair health compared to white individuals. Okay, and then we would report our 95% confidence interval, or you could give a p-value. So because these confidence intervals don't cross 1, they are statistically significant. Okay, and we can see that here. So for example, for Black and Hispanics, you can see that the p-values are less than 0.05. So they are statistically significant, okay? Sometimes, and I hope this doesn't like just confuse you guys more, but sometimes our confidence interval may cross 1 very, very, very slightly and will still have a significant p-value. And that just happens because of the way confidence intervals are calculated. So they tend to kind of cover a little bit more, if you will. And I wish I had like a whiteboard because it would make more sense if I could kind of draw it out. It tends to like cover a little bit more than our p-value. So sometimes the p-value and the confidence interval might not match up. And in that case, for me personally, what I would end up doing is reporting both, and then saying that, it's just borderline significant or something like that, or just, it doesn't quite meet, significance. So, so yeah, if that's more confusing than I apologize. Let's just go back to looking at this other odds ratio. So you can see that it matches up, right? The estimate is less than 0. It's negative, and so that corresponds to an odds ratio that's going to be less than 1. And sure enough, the odds ratio here is less than 1. If we look at our confidence interval, it goes from 0.73 to 1.18. That crosses 1, right? 1 is included in that range, and therefore it's not statistically significant. And then that does match up with our p-value of 0.574. That's greater than 0.05. So then we would conclude that there is no difference in general health, the odds of having fair or poor health for other race ethnic groups compared to white individuals. Okay, so the only 2 groups that are significantly different from our reference group are Black non-Hispanics and Hispanics, and they are at greater risk of having poor or fair health. So this is something that you'll, when you end up, when you start writing out your results for your final project, that's something that you'll want to do. If you run a logistic regression or any model, you would report the odds ratio or whatever the estimate is if you're running a linear regression. And then you could either give the, yes, this is real data, this is NHANES data. You could either give the 95% confidence intervals, which I tend to prefer, because it kind of gives you an idea of how precise an estimate is too, right? So if you look at 1.76 and you look at the confidence intervals, it's pretty tight and centered around 1.76. Sometimes what you'll see is maybe an estimate of 1.76, and then you'll have a confidence interval that goes from like 1.02 all the way to like 40 something, like a ridiculous odds ratio, like 40 something. And I've actually run into this in some of my research. And what that means is you have a very like imprecise estimate of your odds ratio. And typically that can happen if you have like a small sample size, for example. And that tells the reader that, yes, we had a statistically significant odds ratio, but the confidence interval is so wide. And so our estimate isn't really very precise. And so we're going to kind of have a little bit less, place less weight in that result because the confidence interval is so wide. We wouldn't get that information from the p-value because the p-value would just show that it's statistically significant. So my preference in general is to present the estimate as well as the 95% confidence interval. A lot of clinical journals, they also want a p-value. So if that's the case, then I'll also report a p-value. And it might be the case in kinesiology, I'm not sure, where the p-value is more important. You just want to know whether you're rejecting or failing to reject the null hypothesis. So if that's the case, then stick with the p-value. But I would say like in epidemiologic studies, I tend to want to include the 95% confidence interval as well. Okay, so we've run this sort of, like univariate model, right? Where we just have one variable, we just looked at race and how that was associated with general health. So now let's run a multivariable logistic regression. So
I had a quick question.
Yeah, sure.
So have you seen, so I get kind of conflict. So when I read the literature, when I like about status on health when it comes to race and ethnicity, I found that one, I read all the time that Hispanics are more predisposed and have higher rates of like type 2 diabetes and stuff like that. But then when I read about like Filipinos, and I'm assuming that would be like the other, they have like the highest rates. And it's really weird. I essentially read like conflicting data. So when I read about Filipinos, it's like 86%, 76% of them have obesity. And then when you read against like African Americans, non-Hispanic African Americans, and then Hispanics, and then like when compared to everyone else, they have like way lower rates. So like I'm kind of conflicted with this data, and then also like all the other data. Is there any data that you see that like what do you see is to be true, I guess? Like who has the highest rates?
Right. Okay. So there are a few issues going on there, right? And we kind of touched on this when I talked about, like, for example, breast cancer rates in different race and ethnicity groups. Right. So the first thing I'll say is there's always going to be conflicting results across studies because they have different samples. They have different distributions of, these different subgroups in their samples. And then two, researchers might combine subgroups together. So for example, Asian and Pacific Islanders are generally combined in most of our research. And I totally understand why, right? Because we might not have denominator data. So for calculating rates, we need a denominator, right? We need a population at risk. We might not have the appropriate denominator data to calculate rates for those individual subgroups, right? So the census, for example, only in 2010, I believe, did they start allowing individuals to select specific Asian subgroups and then keep them separate. So now we have like at-risk populations for these different subgroups. So, so that is also a limitation where, sometimes we're forced to combine everybody. And what that does is it masks any differences between those different subgroups. So it's not so much that, because, for example, I've collapsed everyone into this other group and it looks like there's no difference between that other group and whites.
Right.
This
Right.
particular analysis in this particular sample, that is true, right? There is no
Okay.
difference. We're statistically showing that there is no difference. However, if I were to look at this other category, and let's just say I was able to break it down by, for example, Southeast Asian, and then, Filipino, and then Pacific Islanders, then I might see differences. I might see that, for example, Southeast Asians, maybe they have, better health. And then Pacific Islanders, they have worse health. But because I'm combining all those groups into other, now it just sort of, they've all kind of merged into looking like they're the same. Like one subgroup is worse, one subgroup is better, and then I combine them. Now they just look like they're the same.
I remember that conversation.
Yeah.
Yeah.
So,
Okay.
yeah. And again, it's not that, it's not like, like let's say for this case, it's not like, oh, I don't care, that there might be subgroup differences. If you remember from table 1, it's also like a small number. And granted, there aren't many more Blacks and Hispanics, but let's say this number was like, I don't know, 100 people, So in that way, I'm almost kind of forced to combine everybody, because if I were to look at subgroups and let's say maybe there's only like 4 people in the Pacific Islander group, that's not going to allow me to make any sort of meaningful comparison. So I'm kind of in that way also forced to combine everybody together. So sometimes it's, we're combining these different groups, these very heterogeneous groups, because I'm certainly acknowledging that they are heterogeneous. Sometimes we're forced to combine them just because of, mathematical reasons, right? For statistical like power, or we just don't, in this case, we're running a model, logistic model, we don't need denominator data, but sometimes we do, if we're looking at rates, for example, and if we don't have that denominator data, then we can't separate those groups out. So the cool thing is, and again, sorry, like going off on a tangent is, for example, I worked in Hawaii for a number of years focusing on disparities research. And because Hawaii is so diverse in terms of their Asian and Pacific Islander population, almost all of the research that we did separated them out. And we were able to do that because Hawaii's state census did actually, collect individual information on these different subgroups and keep them separate. So we had denominator data for those subgroups for individuals living in Hawaii. So, and again, that's sort of, Hawaii is a very diverse state with regard to, Asian Pacific Islanders. And so they, they know that it's important for them to collect that information so that we can kind of look at these different subgroups. Because even within Pacific Islanders, we see differences.
Correct. Yeah.
So,
I hear you.
Yeah, so that's my long answer. Sometimes we're forced to do it, for either statistical reasons or sort of logistical reasons. And then sometimes too, maybe, for example, if someone were to run this study, maybe they're actually, even though they're asking broadly, is there a difference in general health by race? Maybe they're really mostly interested in Black non-Hispanics versus white. And that's their primary, that's really what they're interested in. And then they're just kind of collapsing everybody else into other.
Correct.
So,
yeah.
so it really just depends on your research question. But I'll also say like these findings shouldn't be too surprising, right? And so now let's see if that finding holds when we adjust for gender and age. Okay, so now I'm including these 2 potential confounders. So now I'm creating this object called multiple multivariable logistic regression, and running the GLM. I'm including, so this is our outcome, remember, new race, gender. We also want to tell R to treat it as a factor variable and not continuous, and then age, and then our data set name, and then it's binomial because we're running a logistic regression. All right, so now what does that look like? Okay, so again, these estimates, you know, they're harder to interpret. We need to exponentiate them to get our odds ratio. But this output does give us the p-values. So it looks like there's still, so these are very small p-values, right? They're less than 0.05. It looks like Black and Hispanic are still statistically significantly different than our white reference group. And then it looks like there's probably not going to be any difference for that other group, just like we saw previously. It looks like there won't be any difference between men and women. So this is female compared to male. And then it looks like age is significantly associated. But let's look at the odds ratios so that we can interpret this a little bit more, you know, in a more straightforward manner. So I'm now creating this object odds ratio 2. And this object will include results from the multivariable analysis. Okay. And then I'm rounding it to 2 digits here. Okay, so this is a lot nicer to look at, right? So now after adjusting for gender and after adjusting for age, we see that Black non-Hispanics are at almost twice the odds of having poor health compared to white individuals. And Hispanics have more than 3 times the odds of having poor or fair health compared to white individuals. There's no difference for this other group, right? The p-value is greater than 0.05, and we also see that the confidence interval crosses 1. And the same thing for women versus men. So this we would say, you know, because this non-significant, there's no difference in the odds of having poor health for women compared to men, adjusting for all these other factors. And then we see that there is actually an effect of age, but it's very, very small. And remember, age is like in single years. So that would be kind of, you know, maybe it's hard to interpret, right? Like for every increase in year, there's like this 0.02, you know, like 2% increase in the odds of poor or fair health, you know, so one thing that we're going to do, actually, let me scroll down, is rescale age. Before I do that, I just want to show you that there's one other way that you can display the odds ratios. Let me just do that real quick. And it's using this logistic display function. And then remember, this is our multi-model object from up here. Okay. And so this is kind of nice, right? Because it gives us our odds ratio, our lower and upper limits for the confidence interval, as well as our p-value in a single table. So that's just another nice way to create a table of our odds ratios. And it's nice in the sense too that, you know, so for example, this table doesn't include that p-value. So it's kind of nice that everything is all in one table. So that's just another way to visualize that. Okay, so if you remember, right, age right now is in single years. So the odds ratio is saying for every 1 year increase in age, there's like this 2% increase in the odds of having poor or fair health. And so, you know, it might be more meaningful to rescale age and look at the difference or the change in odds across, you know, 10-year intervals. So I'm going to rescale this. So I'm creating this age, new variable called age rescale. And then I'm just taking age and I'm dividing it by 10. Okay. So now I'm going to run another multivariable model. I'm calling it multi-model RS. And then I'm including this rescaled age variable. Okay. And then I'm going to get my odds ratio table. Now this is, and this makes sense, right? Because for every year increase, there was like a 2% increase in odds. So now we're saying for every 10-year increase in age, there's this 20% increase in odds. And so just a little bit more what's the word I'm looking for? It just makes a little bit more sense, right? Because these 1 year changes, that change in odds is just so small, and it might make, it might be more meaningful if we change it to something like every 5-year increase in age, this is the change in the odds, or every 10-year increase in age, this is the change in odds. So, so that's one thing that we can do if you're interested in really interpreting an effective age. One thing to note is that if you see all these other odds ratios have not changed. So even though we've rescaled age, all those other odds ratios have not changed, and they shouldn't, right? Because we're still adjusting for everything. It's still the same. All we're doing is asking, what is the change in odds for every 10-year increase in age versus every 1-year increase in age, but everything else should stay the same because we haven't rescaled them or changed them or anything like that, and we're still just adjusting for age in our model. Okay. So let me just pause there and see if everybody is, do you feel pretty good about this so far? And I will post this example code so you can go through it, and then you created this NHANES data set for exercise 2. So if you want to run this code on your own, you can do that as well since you have this data set. Okay. The last thing I'm going to do is show you linear regression. I think we did it for one of the exercises, but I just wanted to go through it again here because I do think that a few of you, or at least one of you, will be using linear regression. So let me just include that as well as an example. Okay, so the generic code for multivariable linear regression, it's very similar to this GLM function. You create an object, and then we have this function LM, which stands for linear model. And just like with GLM, you have your output variable, this tilde, and then that's followed by all of your independent variables. So in this case, we have 3, and then we specify our data. Okay, and then we just take a summary of that object to give us the output from our model. So now let's run a linear model, and in this case, I'm going to run it on vigorous activity, which is something we also created in the NHANES dataset. In this instance, I believe this vigorous activity variable includes all of the outliers. We have race, and we're specifying that it's a factor variable. We have gender, also a factor variable, and then I'm including this age rescale variable. So it's basically the same, similar model. So we're including the same independent variables as we are up here. The only difference now is instead of looking at general health as our outcome, we're looking at minutes of vigorous activity per day, and that's continuous. So we're using a linear model. Okay, so let me just run that. Okay. So now we can look at these estimates, and these are actually just the estimates. We're not, transforming them or anything like that because we didn't transform our outcome variable for the linear model. So we don't need to do anything once we have these estimates. We did for logistic regression because remember, we transformed our outcome variable general health with this binomial link. Because we had general health as a binary outcome. So we need to account for that when we are, changing back or transforming back our coefficients or our estimates into these odds ratios. But in this case, for the linear model, we don't have to do anything. This is our final output. Okay, so the intercept in this case, that is going to be your average or your mean daily minutes of vigorous activity when all of the X's are 0. So when, it's just the reference group. So when it's white, male, but then age being 0. And that doesn't really make sense for this particular model since everyone in our sample is older than 20. But let's just say we only included race and gender in our model. Then this intercept would correspond to the mean daily minutes of vigorous activity for white males. Okay, so that's our reference group for both variables. What these estimates then mean are, so we would say, for example, that Black non-Hispanics on average have, perform or do 16 minutes more vigorous activity than white individuals, okay? And that is statistically significant. So their mean vigorous activity is higher than the reference group, which in this case are white individuals, and that is statistically significant. Okay. Here, Hispanics, it looks like maybe 4 minutes, but it's not statistically significant. So we would say there's no difference in average daily vigorous activity for Hispanics as well as other race ethnic groups compared to white individuals. Okay, here we would say that women on average have 21 minutes of vigorous activity less than males, and that is statistically significant. So their average daily minutes of vigorous activity is 21 minutes less than males, controlling for all of these other factors. And then for age, for every 10-year increase in age, vigorous minutes of vigorous activity decreases by an average of 3 minutes, and that is statistically significant. Okay, and if you look here, so I just want to point you to the number of observations that were deleted. We lost a lot of individuals, and if you remember, there were a lot of missing values for vigorous activity. And so that is why, so not only, we would have had to exclude all of those individuals from this particular analysis. Okay, let me see. Okay, that's all I had. So I'll stop there and see if you guys have any questions about the linear regression model. Okay, so just recap, vigorous activity, it's a continuous outcome, and therefore we would use linear regression. I think to the individuals that I sent links to, those links also show you the different sort of diagnostics that you have to conduct after you run your linear model, so you can check that all of your assumptions hold for the linear regression. So for your final project, you would want to then go back and look at like the residuals, for example, are those normally distributed? You can look at the residuals on a QQ plot, for example, to see if that assumption holds, if you run a linear regression model. And then if not, then, you and I, actually, if you find that, definitely reach out to me because running so what we would do if, let's say, linear regression, it's, we violate this assumption of linearity, but we want to run a multiple regression model, we would start to do things like include spline functions or like polynomial functions in our model, which I think is like beyond the scope of this class. So if you run into an instance where you've run your model and you're finding that the model violates this assumption of linearity, for example, or your outcome is not, even kind of close to normally distributed, if it's very, very, very skewed, and actually like vigorous activity, it happens to be very skewed and we have these outliers. If that's the case, reach out to me and we can kind of figure out what to do. And most likely my answer is going to be just go ahead and run the linear model anyway and make sure and include in your final project that you evaluated the assumptions and it looks like maybe this particular assumption didn't hold, but I would still just tell you to go ahead and run that, this linear model anyway, because I think the methods that you would have to use to then sort of account for that, I think are, way beyond the scope of this class. So, so I think it's okay, but definitely reach out to me if you do run into that issue. And then for logistic regression, remember we're looking at general health. That's a binary outcome, just a yes, no. So it might be disease, no disease. That might be an outcome of interest. Then we would use logistic regression, and then you would use this GLM function and just make sure that you specify this binomial link. actually it's a logit link, it's a binomial distribution. Okay, so I will close out of here. I will post this to Cougar Courses so that you can use this and run it if you want to on your NHANES data from exercise 2. Let me just check something really quick. Let me stop share. Okay. Okay, so that's all I had in terms of, showing you an example. And then I wanted to kind of leave the remainder of class to see if, if you folks want to start working on your final project, now during class, or if you want to ask any questions about your, final project, or, if maybe you have an idea of what research question you want to ask, but you're not really sure and you feel comfortable asking in front of the class, we can do that now. So really the rest of this class is for you to, work on your final project independently or ask any questions that you might have related to that or anything else in the class too. So, yep, so the floor is yours. No question.
I had a question on so how would you so in a study, how would you get a generational question I guess started? I don't know how to put it in my manuscript, and I don't know how to show the data, and I don't know, I've never done that. I never really seen it, so I was just curious. Is it just literally just a quick question, what generation are you?
Yeah, so you would ask, are you first generation, second generation, third generation, and then typically after that it might just be fourth or greater. And then
does that influence how I was thinking about that question is, would that have any effect on my data? So I would have everything separated by race, well, I guess by ethnicity, because I'm going to have a Filipino population, but then also I'm going to have generational status as well. So would it be a binomial linear regression? Basically what we just did, would it be the same thing or different?
So in this case, let's say for your particular project, those would both be independent variables, right? So you would have, if you're looking at Filipinos and other races, that would be one categorical variable, right? So you might have Filipino, and then you might even have just other, maybe, let's say, okay? And then you would have another categorical independent variable, and that would be generation status. And so it would be first, second, third, or greater generation. You might, in your model, look at a potential interaction between the two, or you might just keep them as separate independent variables. And then VO2 max being your outcome, that's continuous. So you would be running a linear regression, most likely a multivariable linear regression.
Ooh,
So,
okay.
Yeah. And then if you were to, for example, present in your table 1, then you might want to look at mean VO2 max by these different categories of individuals. So, is there, what are the means or the median, depending on the distribution of your VO2 max? What is that compared, for Filipinos versus other race ethnic groups? What is the mean VO2 max for first generation versus second generation, third or greater? So yeah, you would just present the mean or the median values for those different categories. Does that make sense?
Yeah, I gotta write that down.
Okay. So let me actually share my screen again. Hold on one second. Okay. So let me just scroll up. Okay, so what you might have is maybe you have male, female, you have race, ethnic groups, you have generation status, and then here, this is categorical, but what you might do, let's see, is just have not these two columns, but one column, and you would have like the mean VO2 max. So you would have like maybe in your first row, everybody, what's your VO2 max for everybody? And then you break down. So in this row, it would be like, what's the mean VO2 max for men? What's the mean VO2 max for women? And then you would have a p-value, like a t-test p-value, right? And then for example, if you have more than two race ethnic groups, for looking at VO2 max, if there are any differences across those categories, then this p-value would correspond to an ANOVA, a one-way ANOVA. So yeah, that's how you might consider setting up your table 1.
Got it. Okay.
So let me stop share. And then let me just write a note to myself, like post example code for everyone. Does everyone have a research? So I apologize, I haven't checked my email this morning, but so I may have missed some emails that were either sent like last night or this morning. Does everyone feel pretty good and set with your research questions? Okay, awesome. Okay, so I have in the chat a direct message. Okay. Okay, so let's see. Sorry, I'm just reading the question. Okay, let me just respond to this question. Hold on.
I just posted my question. You could just disregard it.
Okay. Okay. So if this also helps any, basically the example that I went through, looking at the NHANES data and looking at, having this research question, like, is there a difference in general health by race, ethnicity? That would be sufficient for a final project. So basically what we went through in the first half of class would suffice as your analysis for, well, you would want to check your assumptions. So one thing I would look for in your analysis is whether you checked, for normality of your variables. If you're doing like a linear regression, for example, did you test whether the assumptions of those models or whatever analysis that you conducted, did they hold? I would also look for that. But basically what we went through would be sufficient for the research question. It would be sufficient for the actual statistical analysis of the data. So running the multivariable logistic regression model. And then we have a table 1. So that would meet part of the requirement of our tables and figures for the final project. One thing that I would want to additionally include on top of those, testing for assumptions, is maybe I would include a figure. For example, maybe I would plot the odds ratios, and if you end up doing something like that, I can help you with that. So maybe I would have, additionally, like some kind of figure to display my results. And then, in the background section, I might look for, in the literature, look for papers that talk about, general health status or just sort of health, sort of general health, and any differences between, different race and ethnic groups, or, maybe even more broadly, if anyone has looked at disparities in general health by other variables, I might look for papers like that in the literature and then include them in my background section. So typically in a long, I think, hold on one second. So I have a question about how long the background can be. Okay, so in the in a full manuscript, typically our background would be 1 page, but I believe it might, let me just double check to see. Sorry, I'm going to the final project guideline to see what, if there is a length for that specified. Okay, so let me share this screen with everybody. Hold on 1 second. Okay. So you should be able to see this. All right, so this is posted to Cougar Courses. It's in the final project section, and I think that's on like the lower right-hand corner. It's like the last section in the Cougar Courses. So like all the different weeks and then final project. So there's a PDF of this there. So that kind of gives you an idea of how long your manuscript needs to be. So this write-up is actually going to be a little bit shorter than sort of a full manuscript that you might submit to a journal. So it looks like this will be a 4 to 6 page scientific manuscript that includes these sections. It gives you guidelines for how to format that. Okay, so you want at least 2 tables and 1 figure. Okay, you want to cite at least 8 peer-reviewed sources. Let me just see. Okay, so it says, okay, so your background or purpose in this case is just going to be, okay, wait, no, that's for your abstract, sorry. Sorry, I'm just scrolling down here. Okay, so it looks like a typical manuscript, it would be, you know, a half to 1 page. So this is actually a little bit shorter. So typically in a full manuscript, we might have like at least a page for our background section. For this particular final project, you would have a half a page to 1 page. So it's going to be pretty short. So if you reference that final project document, that will give you kind of a guideline in terms of how long each section needs to be, the minimum number of tables and figures to include, as well as the minimum number of papers to cite. Okay. Let's see, let me just scroll up and make sure. Okay. All right, and then I got you, Alex. I'll check my email so that we can talk about that. Okay. Any other questions? Let me stop share.
When's your meet?
So they announced the workouts on May 6th, I believe, which is a Thursday. And then we have until Monday to do all of the, I think they give us like 5 or 6 different workouts. And then we have like that weekend and we submit all of our scores on Monday.
Is it like is it like 500 burpee or like what type of workouts?
So generally so the individual athletes already had their like quarterfinals. It was like this past weekend. And so like looking at those workouts, I don't know, it's just like a mixture of like lifting heavy weights and doing some kind of, you know, metabolic, you know, conditioning type workout. So it might be like, I don't know, box jumps or like handstand walks or
You can do a handstand walk?
yeah, I do.
Oh shit.
Yeah, like, but my biggest limitation is I'm not very strong compared, like, and I say compared to like these other athletes because I think, I don't know, yeah, it'll really sound funny when it comes out. Like, I think I'm strong, but I'm definitely not as strong as a lot of these other athletes. Like, they're just crazy strong. So,
how much do you weigh?
Let's see, I'm probably like 125, so I'm not very heavy. But yeah,
wrestled.
no, never. But yeah, some of these athletes can squat like these, and these are like women athletes, like can squat like over 300 pounds, and like it's just like they're just so strong.
Yeah, my wrestling partner when I was 135 was a 125. She's a New Jersey state champ, and she was insanely strong. Like,
Yeah.
tore me apart all the time. It was insane.
Yeah, it's really impressive. I think like for me, I'm just basically gonna go into that weekend and just try not to die. So yeah. So
Survival.
yeah, exactly. So I'm just happy because it's pretty cool. Like I don't work out at a gym right now. We have like we have a lot of equipment on our patio, so that's basically all I'm doing. And then yeah, like I think having like these two kids, the younger one being like 15 months old, I'm like, all right, this is like it was pretty successful this year. So maybe next year will be better. We'll see. I need to work on a lot of strength, basically, what I need to do over the next year. But yeah, thanks for being interested. It's just really silly. It honestly, when it comes down to it, it's like I always joke about it. It's like, all right, okay, I'm good at exercising. Like, yay.
Yeah,
So
but
yeah, it's pretty silly.
it's like, it's funny though, because like, I mean, you feel that, right? But it's like you are like 1% of the population, and
Yeah.
it's really interesting.
Yeah. Oh, I appreciate that. Thank you. So the best part for me, honestly, is looking at where my weaknesses are. So, like, what can I be better at? And I know for sure, like, I need to work on my strength over the next year. So that's what I need to focus on. So it's kind of cool because it's like, where are the, holes in my fitness and like, what can I do better? So
VO2
yeah,
max, VO2
yeah,
max. That'd be a great
yeah.
start.
I would be very interested. I would be very interested in knowing. So, um, but yeah, any other questions? I know these are shorter classes. Maybe, now that you have your research questions, and I will check my email and respond to everybody by the end of the day, and also send back out your exercise 3. And then I think next week, I'll check the syllabus, but I think at that point by next week, I would ask that all of you have your data sets in mind and we can kind of work through them, during class. And then that way, if you need help or assistance with an analysis or your code isn't running, I can create like a breakout room and then, we can look over your code. So yeah, and unfortunately it's like all virtual, which is not ideal. But I think this is what, and I like that idea, Dr. Armenta had in mind where when he's taught this class in person previously, like this is what you would do. And then he would just kind of, walk around and help you guys out.
I do have a couple questions.
Yeah, sure.
Really quick. So I know we've talked about this a bit before, but the main thing I'm studying is where surfers feel cold, but then I can also look at like comfort and where they think they're want to be warmer, whatever. All that makes sense to me. But then if I wanted to look at more of like a subset data, so if I wanted to look at like just women, and then like thermal comfort and perception can vary on like various cycles or like various phases of the cycle. So if I wanted to do that, would then I have to do a power calculation of the women to see how many I need to power that? Or am I just gonna I'm just not entirely sure how that would be like how would I make it valid, I guess is what I'm asking.
Okay, so you already
that makes sense.
Yeah, it does make sense actually. So you have do you already have like a full data set, or you already have in mind like how many individuals you will be in like recruiting into your study?
So that's so I mean the goal is to get at least 500.
Okay.
I only have 50 right now, and then out of the 500 it's kind of just like random, men or women. I don't have a goal of like half and half.
Okay.
Just because that's not really like an accurate representation even of like the surf demographic.
Okay.
So unfortunately, but yeah, so I actually don't know how many, I don't have like a set goal of how many men or women I want to get.
Okay, so what you might end up doing is, since your primary analysis for, it sounds like since you're collecting both men and data for men and women, your primary analysis isn't focused on women, right?
Correct. Yeah, no, it's just like overall
okay.
Of my whole entire data set.
Okay, so then in that case, you're kind of you know, whether it's like fortunate or unfortunate, you just have the women that you end up with.
Right.
And then you would run your subgroup analysis. And I think that's like a really interesting question, right? Because like I know pain perception can change like depending on time of the month and everything. So I wouldn't be surprised if like, you know, temperature sensation also changes. So then once you get the results for that, you can go back and look at like based on the sample size and based on the type of analysis I did, how much power did I have to observe this effect size versus this effect size versus this effect size. So you would basically be doing, right, exactly what you said, like a power analysis versus like a sample size calculation. So you already have a set sample size, and then you can actually go back and look at how much power did I have to detect this particular difference. And I can try to help you out with that. So typically, I know it sounds bad, but typically for like power calculations, we leave that to biostatisticians because it's like really boring. And also like kind of complicated actually, you know, so you know, usually what I'll do for like my projects is I'll reach out to our biostatistician. He's like our consultant, and I would just say, okay, I'm running a survival analysis. I have this many people. I want to observe a hazard ratio of this, and I have this many covariates in my model. Like, can you help?
It's quite complicated.
And actually, he'll have one of his students do it for him.
Oh, great.
Yeah, like one of his postdocs or something. Yeah. One of his like, postdoc or grad student. But yes, we can go back and I can help you with that. So there are like programs that like PASS, for example, that will help us do that. So yeah, so I'm happy to help you out with that.
That would be great. And then, so on that topic, if I decide I want to look at different variables, like look at length of surf session versus where someone felt cold or comfortable, uncomfortable, or air temperature or water temperature, would that be the same problem that I have of needing to look at like effect size, or because that,
no.
So what I guess my question is, do I have to do it for every single like subset of things I want to analyze?
Oh God, no. Okay.
Okay.
So what I'm hearing from you is that you probably will end up running some kind of multivariable model.
Right.
And, you know, temperature, like perceived temperature being your outcome. So it's probably going to be a linear regression model.
Right.
And then what you could do is just say, okay, your primary research question is there a difference? And you have all women. So is there a difference in temperature perception by, you know, like placement in one cycle? So that's going to be your primary independent variable, or your primary exposure variable of interest, if you will. So you would just need to do a power calculation for that. In your power calculation, you'll also specify that you have all these other variables that you're going to include in your model. And then that power calculation will account for that. And then you don't need to worry about doing a power calculation for those other variables because they're kind of like secondary to your analysis. Yeah. So
that makes more sense.
Kind of like how we did with this NHANES data, we looked at the odds ratios for those other, for like gender and for age, but really our primary interest was looking at whether there were differences by race, ethnicity.
Okay, that makes more sense then. Cool.
Thank goodness, because it would be really awful.
No, I'm already very overwhelmed, so I just don't want to create more work for myself than possible.
Yeah, no, absolutely. I totally understand that. Yeah.
I appreciate the help. I'm sure I'm going to have many more questions as the days go on. Awesome. Thank you.
Okay. All right. Does that sound good? I know it's like pretty early, but if you don't have any other questions, then I can let you get to it, and you maybe like, I don't know, use this time to start working on your projects or, okay. And yeah, and I totally understand that this is, I think we have like maybe like 5 weeks left in the semester. So I know it's like pretty quick here in terms of, you know, writing everything up and putting a poster together. And then, yes, you'll present in class with your poster, but it is very informal, and I think all of you know each other. So hopefully you're all comfortable with each other too. And it's just like a 2 to 3 minute like elevator speech about your project and your results. So it'll be, pretty casual in that way, not super formal. So.
Thank you.
Okay. Okay, so Alex, I'm going to have one student stay after everybody leaves. If you want to stay for a few minutes and wait after that, that's totally fine. Or we can also chat on Friday during office hours, but I'm sure you want to like meet sooner. And okay. And all of you, okay, sorry. So I'm reading your message, Amanda, like you all know each other on Zoom, right? Because it's been a year for this pandemic. Okay, that really sucks. Okay, so I have the 2 students who are direct messaging me stay behind. And then, let's see. Actually, okay, so I want it to be private for both of you. So what I will do, if it's okay, I'm going to direct message you. And then, hold on one second, Alex. Okay. And then for the second student, I just messaged you. What I'll do is reach out to you. So go ahead and like log off. And then once I'm done speaking with, breakout rooms. Okay. Let me see if I can. And thank you so much, you guys, because I'm not tech savvy. So let me see. Oh, breakout rooms. Okay, awesome. Okay, assign manually. Okay. Okay, so both of you stay on. I'm going to assign person 1 and then person 2. Okay. Awesome. Okay. Did that work? Oh, yes, everybody is good to go. And please, like use this time to, I don't know, like recover from the weekend or work on your projects. But yes, you're all good to go. Okay, thank you, Svetlana, for the reminder about these breakout rooms. Okay, so everyone's good to go.
Thank you.
Except the 2 students. Thank you, Sebastian.
Thank you, everyone. See you later.
Thank you. Okay.
Thank you.
Okay, so I have the breakout rooms. Let me just try something, okay? So I'm gonna go into breakout room 1. Okay, so you've been invited to join your breakout room. And then, okay, awesome. Okay. Let me